a lecture on priority queue. So you will see an application of heaps, like a main application of heaps, which is the abstract data type priority queue. So a priority queue is an abstract data type which is very similar to a regular queue. But in a regular queue, we had the first in, first out. Like it means that whatever element that was inserted first, that was pushed first, was popped first as well. But in priority queues, every element has a priority, or we call a key value associated with it. It means that the queue is ordered according to some priority value, and we pop the elements, we remove the elements based on their priority or based on their key value. In a priority queue, an element with high priority is served before an element with low priority. And if two elements have the same priority, they are served according to their order in the queue. While priority queues are often implemented with heaps, they are conceptually different from heaps. So priority queue is an abstract data type that can be implemented in many different ways. Like it can be implemented using ordered arrays, unordered arrays, linked list, ordered or unordered linked list. It can be implemented using binary search tree. So like heap just provides a good implementation of priority queue. A heap that uses an array-based representation of a complete binary tree is a very good implementation method for priority queue. If you know the maximum number of items that will be stored at one time, at any one time. So in this picture here, you see that just like the difference between a standard queue and a priority queue. The only difference is that like the data are removed in priority queue based on elements priority. A priority queue is a data structure that allows at least following two operations: insertion and deletion. Also like same as like pushing and popping, we also like have peeking, right? So like it also like provides like all these functions. Inserting is the equivalent of enqueue, like which we discussed like when we talked about queues, and delete is equivalent of dequeue. So like in the delete part, like we can either find or return and remove the minimum or maximum element in the priority queue. So like when we talk about priority, our priority can be either like the key with the smallest number is going to be removed first, or like the element with the smallest key is going to be removed first, or it can be the element with the largest key value is going to be removed first. So like that's like how we decide if we should implement a min heap or a max heap, right? So a dequeue gets element with the highest priority, where priority is based on a comparable value, right? So like the priority that we assign to every element is based on a comparable value. What does that mean? It means like it's something that we can compare. It's either a number or like a character that we know, we can assume, we can like figure out very easily which one is bigger, which one is smaller. It can be either a smaller value, higher priority, or higher value, higher priority. So here you see that here, whenever we insert elements, like we have like a data part, which is X, that we want to insert. We also provide another parameter, which is called key, right? Which is the same as the priority of the element, right? So every element that is enqueued into the priority queue has a key part. So we say it has, excuse me, it has a key value pair. So some of the applications of um, priority queue, some of these are real life applications, like, and some of them are programming applications. So for example, like for lineup of incoming planes at the airport. So like you might like the people in charge of that like might have like some priority for every plane, like and like, or like a printer, like it might have some, like it might assign some priority to every job that he has to do. Like let's say like if he has like shorter documents that can be printed very fast, they might have higher priority. Or like jobs queues, like if you have like multiple tasks to finish, and like you give priorities to your tasks. So for example, like for your courses, you might have several assignments and projects, and based on the importance of the course or the importance of the assignments or your grades, or like the number of days that you have to the deadline, you might give certain priority key to each of these assignments. Or let's say like if a server that has to serve multiple clients, right? So like she or he might assign certain priority to each task, right? Like if a task like can be finished very fast, like you might want to give that higher priority. Or if you have like a very important client to serve, you might give that client a higher priority. In operating systems, like multitasking is needed. Like there are several tasks, several processes that have to be processed. So operating system runs or dequeues the shortest job. Like it might do the shortest job first, like, right? So like that's one of the ways that operating systems give priorities to certain processes. The processes are given relative priority of execution, so that the process with the highest priority in the process queue is the first one to be executed when the processor is free. Another application that some of you might have seen, that in the emergency room in hospitals, the staff there assign a priority to each patient, and this priority is not necessarily based on first in, first out, right? It might be based on the severe, like how severe, like you are sick, or like how hurt you are. So like it might override the time at which patient arrived. When you want to get on a plane, when you want to board on a plane, you've seen that like usually seniors or people with children, or soldiers, veterans, like they get higher priority. So like in networking and communication, in packet routing, there are also like priorities assigned to each packet, the data packet that is communicated or is transmitted. So like some information might have higher priority than the others. And you can think of a normal queue, like a first in, first out queue, as a special case of a priority queue, that like your priority is based on the time of arrival. Um, a priority queue stores a collection of entry, like elements. An entry in a priority queue is a simply key value pair. So the value is the part that we are interested in, and the key is the priority that is assigned to that entry. When you want to determine the priority for your assignments, you need a value for each assignment that you can compare with each other, right? So let's say like you want to figure out which assignment you should do first, right? So there are multiple factors that you have to consider, and based on all those factors you might give like a relative key value or a relative priority to your assignments, right? So that priority is basically called key. A comparable, so a key is a comparable object. So like this is very important, it has to be comparable so that like we can compare the key of different entries, different tasks, different elements. So a key is a comparable object that's assigned to an element as a specific attribute for that element, which can be used to identify, rank, or weight priority of that element. Priority queues stores entries to allow for efficient insertion and removal based on keys, right? So like the keys are used to like provide a very efficient removal like method. Recall that when we insert an element into a priority queue, we need to assign a key to that element. So like this is like something that for priority queues we have to know, that like every time we want to enqueue something into the priority queue, we have to assign a key to every element, right? Like in the heaps, like we had max heap or min heap, right? So the value of the element itself was the key, right? The higher the value, it was removed first, right? You saw that like in the max heap, right? We removed the root, right? Which in the max heap was the highest number. So like in that case, key was basically the value of the element itself. But that's not always the case. Like it might be just like a combination of many different factors, and the elements will be extracted based on their key. So here you see an example that like we have an empty priority queue, right? And then we insert an item, right, which is A, and the A has priority 5. And then we insert another item which has value C and it has key value 9. So this is the priority, right? And like we keep doing that, we keep enqueuing, we keep inserting, right? So like you see that like here, like we have the like the higher priorities, like you see like in the priority queue, like the element or the entry that had the value C has the highest priority, although it wasn't the first one to enter, but it would be the first to be dequeued, right? Like if we are doing based on this the higher priority, sometimes we do based on the lower the priority. So this case is based on the lower priority, I think. Like let's go see like how this is done. Minimum element, right? So like here in this one, we just like want to know which element has the lowest priority. Which element has the lowest priority? So it was the B. So like we just like this, get this one in the B. This is basically a constant method. Like it doesn't change our priority queue, just give us the entry with the lowest priority. Minimum key like gives us the priority, like the lowest priority of all the entries that we have in our priority queue. Now here we say like remove min, right? So here the entry with the lowest key has the highest priority, right? So like here when we say remove min, right, we mean like we're just gonna remove the entry, like we're gonna dequeue the entry with the lowest key value. So like here B is gonna be dequeued first, although it wasn't enqueued first, but it was gonna be dequeued. It's gonna be dequeued first, right? Size, it's going to give us the number of entries that we have in our priority queue. And again, we have some remove min, right? So like it's going to remove 5 and then remove A because it has the minimum key value, and then D, and then C, and the last one result in an error because like our priority queue is empty, so we can't dequeue anything anymore, right? So like for these cases, we have to write, we have to throw an exception, or like, yeah, so like this is the case that we have to throw an exception, right, if we don't want to get a runtime error. And another one like is basically a Boolean function that would tell us if the priority queue is empty or not empty. So there are several methods to implement a priority queue. We can implement priority queue using arrays, sorted or unsorted. We can do it like using linked lists, sorted or unsorted. We can do it using binary search tree. We can use it like using, like, for example, AVL or red black tree, which are balanced binary search tree, or we can implement it using heaps, right? So all of these, right, like have certain time complexity for insertion and removal, right? So for example, if you have just like a unsorted array or a sorted array, your insertion or removal might get like faster or slower from one implementation to another implementation. I'm going to show you a table that that compares like different implementations and how fast or slow you can insert or remove data. So a priority queue is basically an abstract data type that we want to have to have like fast insertion and removal, right? So both of them. So we need to have a compromise, right? In many cases, like you might have different like applications, and like one of these might be preferable. So like you might, instead of heap, you might want to use like another implementation method. So the main criteria for choosing the implementation method is the time complexity for push, pop, and peek operations, right? So like I'm using the stack terminology, but like it's the same as enqueue, dequeue, and peek operation. Other criteria are like how complicated is the implementation of these methods. So for example, we saw that like AVL trees like are not very easy to implement, right? So like it might be advantages to use them, but like, is it easy to implement, right? How complicated it is. Do I need to store extra data to do a search? Do we need to have extra memory spaces, right? So like what is the auxiliary memory complexity? And so for most of the time, like if we know the maximum size of the priority queue, right? If we know the maximum size of the priority queue, an array-based implementation of binary tree, so like which is a heap, right, provides like an array-based implementation of a complete binary tree, which has partial ordering, provides a good compromise between insertion and removal times. So using a heap, we saw that both insertion and removal from a heap can be done in log n operations, right? So that provides a very good um, implementation method for priority queue, because relatively we can like insert or remove data from a priority queue fast, like relatively fast, like because it's going to be in the order of log n. Some of the functions that we want to have for our priority queue, which is very similar to what we had for a regular queue, just creating the priority queue, emptying the priority queue, or removing the priority queue, just having some Boolean functions like letting us know if our priority queue is empty or full, and more importantly, find like inserting or deleting and also retrieving the data with the highest priority. So like not changing the priority queue, but just basically like picking, right? So like basically finding the item or the entry with the highest priority. So these are some of the typical operations that we have for a priority queue. This table like provides a good comparison between like among different implementation methods for priority queue. So you see that if we have an ordered array, right, the insertion, it's going to be in the big O of n. The removal, it's going to be very fast, because like we can just like it's going to be either it's going to be the first element in the array, so like it doesn't take that much time, right? Finding is also like big O of 1, right? So this is fast, but the insertion is um, time costly. The same thing for ordered list. For like unordered array, there are or unordered lists, there are a lot of like insertion is going to be very fast because we don't care about order, right? So like we just insert like in the beginning or in the head of the linked list. But when we want to remove, we have to do a search, and we might have to do a lot of shifting, right, when we remove, right? So like this is both of them are going to be for removing and finding. It's going to be of big O notation. And for binary search tree, um, both insertion, removal, and finding are going to be log n. The same is true for AVL3. Like we covered like all of these functions for BST and AVL3 in previous videos, right? So you should remember why this is the case for BST and AVL3. Now for heap, the insertion and removal, as we saw in the previous videos, they are of big O notation log n, because it depends on the height of the heap, right? And the finding the maximum and minimum, like here, like we are not changing the priority queue, we're not changing the heap, right? So we're just basically picking or like returning the entry at the root of the heap, right? So this is big O of 1, right? So you see that like heap is very easy to implement. Like it's just like based on array, like array implementation of heap is very easy to be done, and it provides a very good time complexity for both insertion and removal, and also like a very good time complexity for finding either max or min. And depending on like on our application, we might want to use max heap or min heap, right? So like we can find the remove the max, remove the um, excuse me, remove the element with the highest queue or with the low, so with the highest key or the lowest key. So basically giving the highest priority to lowest value or to the highest value. So that's like why like I here like I say remove max or min, like based on like the application we might want to implement it using a max heap or a min heap. Priority queue operation and heap operations are very like similar, as the priority value in a priority queue corresponds to a heap item's search key, right? So the priority value that we have is basically the value that we use to do ordering of the heap, right? So priority queue implementation can reuse many of the heap class member functions. One disadvantage of heap implementation of the abstract data type priority queue is that we need to know the priority queue's maximum size. But some of the advantages are like it's the heap is always balanced, and because of that, the height is always log n. That makes sure that the insertion and removal are both in order of log n. It's very efficient for most application, and it's very easy to implement, especially the array-based heap. So like here, like I provide some common priority queue operation. So like we want to create a priority queue, right? So like it can be just like a constructor, can be default, non-default, copy constructor, find the minimum, right? So like this is like a constant member function that would just returns the either the smallest or largest element according to the key field. Okay, like we have to provide key value to every entry or every element. Insert and delete, right? We might want to change the priority of a certain element, right? So we want to change the priority of a certain element. We want to find the number of elements in our priority queue or in our heap. We want to know if our priority queue is empty or full. Sometimes we just want to clear our priority queue. So just reset the priority queue, deallocate everything, right? Or like remove everything from the priority queue. Some other operations that are not as common, and so like just like combining two priority queues, right? So, or returning the position of the element in the heap with a certain key value. Okay, so these are like some not as common operations, but like sometimes they're needed. And like if they're needed, like maybe like a different implementation would be more efficient than heap. Okay, so here you see um, um, implementation of priority queue class using heap. You see some of the member functions that we have, like constructor, enqueue, dequeue, finding the size. Like here, like size t, like if you're not familiar with this one, is like basically similar to int, right? So like you just like don't panic if you see this one, like it's very similar to pic, just like the size of it is different. The number of bytes it has is different. So like here you see like we know like the size of our priority queue, okay? And like so like you see that like many of the operations that we had for the heap class, we can reuse it. So like bubble up or bubble down, like finding left child or right child, finding the parents, like we saw all the formulas for that in the previous videos. Swapping like two different entries, two different elements, or like other member functions that I mentioned here, like so all of them can be implemented in the priority queue class. Here I provide like the definition for some of these, like right, so like for enqueue and dequeue, right? So you see like this is very similar to like it's basically the same as like what we did for heap, insertion and removal. We just have to make sure that when we want to enqueue, our array is not full. So like assert is basically a function that just makes sure to do that. Like, or you can, instead of that, you can throw an exception. Or sometimes if your priority queue or your array is full, you might want to increase the size of your priority queue by making it double the size, right? Or like changing the size, increasing the size. The same thing for dequeue. We just have to make sure that when we want to dequeue, our priority queue is not empty. Here you see the implementation of this is bubble down, right? We saw this in the heap video. We can do the same thing for bubble up. And what else, like swapping two different elements, right? So like this is like what we see here, the constructor and so on. Priority queue has the method remove min, right? So like this is basically the removal method, like this is like the delete method, right? To remove and return the element with the smallest key. So like here it can be either like if this is for a min heap implementation, it can have like also max heap implementation. So like it can be remove min or remove max. So sometimes you want to remove the smallest key first, or like you want to remove the largest key first. This fact makes priority queue useful for sorting as well. So like we can like this is basically the same concept as heap sort, right? So like using, like if you have a priority queue class, you can also like do heap sort as well. So like this is basically what we did in heap sort. Like basically this is the construction phase, right? We make a priority queue and then remove the items one at a time based on their key value. So this is like the sorting that based on heap sort algorithm. One last thing I wanted to mention here is that the standard template library also comes with heap and priority queue classes. So you can just like check these links here to just go through different functions that are provided in these classes. So in many applications or in many problems, we don't want to go through the hassle of creating our own class. So like you might be able to use the standard template library. So like these are the two examples I got from these links related to the priority queue and heap standard template library classes. Thank you so much. That's it for heaps, heap sort, and priority queue.